there was another title that I thought about, but it was nicked, which is Who's Afraid of the Big Black Hole? But this one is perhaps better. And I put this No Need to Be Afraid because there seems to be some sort of feeling that black holes sort of travel around the galaxy, hoovering up things in the way, you know, not very nice things. Have you all heard that? I mean, you wouldn't think that because you're all intelligent, but a lot of people do. So I thought I would try and stamp that problem out right at the beginning, literally so you can relax in the hope that within the next hour you'll still be here. So, supposing our sun suddenly, instantaneously became a black hole. Well, of course, 8 minutes and a bit later, it would get very cold and dark and we wouldn't live very long. But nothing else would happen. The Earth would continue to orbit where the sun had been, where the black hole is, because the gravitational forces of a solar mass black hole would be identical. So in that sense, unless you get very close and aren't moving quickly, and there'll be more of that later on, and not moving in the right direction, you're fine. They don't really hoover things up. In one sense, they're actually better. It would be better for our solar system than actually having the sun. Look at this. I need to make it work. This is a comet that's about to commit hara-kiri. The sun is up here, and it's going right into it. Now, comets come very, very close to the sun, and if their orbit brings them sufficiently close to the barycenter of the solar system, very in the middle of the sun, basically, if they get too close, they'll actually go into the sun, and that's their end. And the sun's pretty big, but if that was a black hole, it would only be about 3 kilometers across. And so most of those comets that now get gobbled up by the sun would survive. So you could say that's better. Anyway, so don't worry about it. We should be here in the next hour. Okay, well, what is a black hole? To be honest, the easiest way to think about it is simply using Newtonian physics. You don't have to worry about Einstein. And I expect you all know that if you fire a rocket off from the Earth with a speed of 11.2 kilometers per second, or 25,000 miles an hour roughly, it will actually leave the Earth. It's got enough energy to escape the Earth's gravitational field. It's called our escape velocity. Now, don't worry about this complicated formula, except to notice that V gets bigger if you make the mass bigger. That's pretty obvious, I think we'll see that. But also, if you actually make the size, if you take a given mass and make it smaller, the escape velocity also goes up. And those are two things we need to bear in mind. So, supposing you made the Earth of lead, what would happen to the escape velocity? Well, V is proportional to the square root of the mass, so also proportional to the square root of the density. We know what the densities are, 5.52 for the Earth and lead 11.34. So all you have to do is to multiply 11.2 by the square root of that ratio, and you get 16 kilometers per second. So if you kept on making the Earth more and more and more dense, the mass would go up and up and up, and eventually V might reach the speed of light. Now, it was Pierre-Simon Laplace who realized this and pointed out that if you had a sufficiently large mass in a sufficiently small volume, the two things both matter, then the escape velocity would exceed that of light, and so not even light could escape. So they didn't really know what to call these objects then. Frozen stars was a name that some people had. And it was John Wheeler. He was one of the world's top physicists in the last century. He came up with the idea of wormholes, and also that wonderful definition of time I teased you with a year or so ago. Time is nature's way of preventing everything happening at once. I did ask you if anyone could come up with a better definition. No one's come to me yet. So he was a great man, and he coined the name black hole for such an object, and that name, of course, has stuck. A black hole can be of any size. It's simply the amount of mass within a certain volume that counts. The more mass, the smaller volume, the greater this so-called escape velocity comes. They can vary in size from the incredibly small, 10 to the minus 18 of a meter. It's possible that such tiny black holes are created when very, very high energy cosmic rays enter the Earth's atmosphere. and even that the Large Hadron Collider might produce them. It was pleasing to see last week, actually, that two Americans who put up a court, or went into court to say, you've got to close the LHC down because it could destroy the Earth. Their case was thrown out only because, in fact, they were the twits, and they basically took it to an American court, and the Americans said, well, there's nothing we can do about it. So anyway, it's going on, and if you're worried about what might happen, all you have to do is to go into www.hastheLHCdestroyedtheearth.com, and yesterday it said no. So I've made that joke, but that does exist. There are two websites that both of them do that. So we're okay, and the reason, as we'll see later, is that such little micro black holes evaporate incredibly quickly. We believe there are a lot of black holes whose size is the order of 10 to 30 kilometers. And those are ones, as we shall see, that are formed from giant stars. So we think there are a lot of those. We also know of black holes whose size exceeds 100 times that of our solar system. So there's an incredible range of size of black holes. If the Earth became vastly more massive, or vastly small, if you could squash the Earth down to just 3 centimeters in size, the escape velocity would actually equal the velocity of light, and the Earth would become a black hole. But supposing we just made the Earth more and more and more dense, its mass went up and up and up somehow, but the size stayed the same. When the escape velocity reached the velocity of light, nothing can go away, and that surface, the surface of the Earth in that case, is called the event horizon. That's the name of it. It has a radius, which in that case will be the radius of the Earth. That radius in general is called the Schwarzschild radius. So there's an event horizon. You'll see why it's called that. Nothing can come out. Things can obviously still go in. Now, of course, our Earth could not withstand being that massive and that small. Gravity would make it collapse, and we'll talk about that very shortly. And again, another formula, don't worry about the details, it just tells you that the Schwarzschild radius, which is the size of the black hole, is simply proportional to the mass. That's all you need to know. So the more massive, the bigger, and it's just a linear, simple relationship. Now, that's all basically Newtonian physics. It's all we really need. Einstein's view is simply that if you put mass into space, or space-time, it curves the space, and as a result, the space begins to become slightly curved. Light will travel in curved lines, as we shall see later, and as you've seen before in my lectures. So eventually it becomes so closed that photons, or anything else for that matter, simply cannot escape. So it's when space closes in on itself. But Einstein's equations, I think there are 12 simultaneous equations, and certainly I don't know how to solve them. You may know the story, Eddington, Arthur Eddington, very famous. He was one of the first people to actually look at Einstein's equations and be able to solve them. And he was asked, Arthur Eddington, we believe that you are just one of only 3 people in the world, apart from Einstein, who can actually solve his equations. He didn't reply. I said, well, why aren't you telling us? He said, well, I'm trying to think who the other 2 are. So they're not trivial, I promise you. Anyway, the ideas are the same. So, what type of black holes do we have? Well, we know about what are called stellar mass black holes, the remnants of giant stars, and we'll talk about those first. We've also known for a long time, from the 60s really, about what we call supermassive black holes. These are things that reside at the center of galaxies, maybe many billions of solar masses. And I've left them last because only relatively recently have astronomers become aware of what we now call intermediate mass black holes. And again, there may be some very, very tiny ones that are caused by cosmic rays. So let's have a look at the various types. So, stellar mass black holes to start with. Well, our sun, looking fairly active there, it's actually beginning to wake up out of its stupor for the last few years. It's producing its energy, as you all know, by nuclear fusion that carries out in its core, which is about 1/10 of a solar mass. Now, eventually, all the fuel will run out. The hydrogen turns first, as now, into helium, then the helium into carbon, the carbon into oxygen, and perhaps a bit more. But eventually, you can get no more energy out. And then gravity makes that core collapse. And it ends up as what is called a white dwarf. It's the little white spot in the center there. Can some of those lights be turned off just to make the pictures a bit better? It would make them slightly easier. So that's great. That's the little white dwarf in the center. It's about the size of the Earth. So gravity is crushing what's left of this 1/10 of a solar mass core downwards to make it much smaller. But eventually, that stops. And it stops because of a quantum mechanical effect, which is called electron degeneracy pressure. Essentially, electrons don't like being squeezed too close together. And there comes a point where the whole mass is sufficiently compact so the electrons say, hey, no more, we're stopping. And that basically prevents any further collapse. So that's what happens to stars like our Sun. If you have more massive stars, they tend to end their lives in rather more spectacular ways. We call them supernovae. And the core in those cases is more than about 1.4 solar masses. 1.4 solar masses is essentially the maximum mass that electron degeneracy pressure can support. And that was worked out way, way back by a 19-year-old called Chandra in India. So what's left, perhaps a solar mass or more, 1.3 solar masses, 1.4, 1.5, collapses down far and far and far more. Eventually, it stops collapsing when its diameter is about 20 kilometers. As the gravity compresses everything together, the electrons and the protons fuse to form neutrons. So the whole thing becomes neutral, and these things are called neutron stars. And in fact, that actually is the image of the neutron star, right at the heart of what's called the Crab Nebula. What stops that collapsing any further? Well, it's called neutron degeneracy pressure. There comes a point when the neutrons do not want to be squashed any closer together, and they will provide sufficient force or pressure to overcome or to balance the gravitational forces. So that's the second point where we get some stabilization due to quantum mechanical effects. What happens if you have stars that are even more massive? We believe that if the mass of the core is greater than about 4 solar masses, not even neutron degeneracy pressure can prevent gravitational collapse. So what happens then? What happens to the most massive stars? Now, Einstein's theory of general relativity is a classical theory. And if you solve the equations, as I cannot, you find that the mass would shrink down to a singularity of 0 size and infinite density. Have you all seen and read that? If you look in all the places you look, you'll find that that actually comes up most of the time when people talk about black holes. And I just don't believe it's true. At the extremes of pressure, temperature, density that we have at the heart of whatever there is, classical theories won't work. Quantum mechanics, as in the case of stars like our Sun or heavier stars, that must come into play. And there is a name for a theory that says what would happen. It's called quantum gravity. It's only a minor problem that no one's actually managed to produce one yet that's widely accepted. So, in fact, you do begin to read, if you search around a bit, that people don't really believe there'll be a singularity at the heart of a black hole. Singularities happen when the theories break down. Einstein's classical theory cannot tell us what's at the heart of a black hole. So he says that the matter will actually contract down to a singularity. Now, I'm going to really stick my neck out here, and I don't think anyone's ever tried to do this before, but let me try and tell you what I think might happen. And this is probably total rubbish, but it's interesting anyway. Now, what we know is that neutrons are made up of quarks. Do you all aware of that ish? That a neutron, because they're neutral, has got one up quark, which has a charge of plus 2/3, and two down quarks, they've both got a charge of minus 1/3. So plus 2/3, minus 1/3, minus 1/3 gives you 0. So they have 0 charge. So that we do know. I think everyone's happy with that. We don't quite know how big quarks are. No one's managed to measure it yet. But it's generally reckoned that they have a size of order 10 to the minus 18 meters, which is pretty small. In contrast, neutrons have a size of order 10 to the minus 15 meters. And I think you can all see that's a factor of 1,000, yes? Now, if you've got a factor of 1,000 in terms of the diameter, say, I know it's a woofly thing, but supposing there is, then the volume goes as the cube, right? So the difference in the volume of quarks and neutrons is in fact 1,000 cubed, which is basically 100,000 million, 10 to the 9. Is that fair enough? So, interesting question, I thought to myself. What might the mass at the centre of a 10 solar mass black hole, how big would it be if it were in the form of a concentration of quarks? Now, it may be a silly question to ask, but I thought it was fun. Now, you don't need to any clever maths for this. We do know that a 1.4 solar mass neutron star has a radius of 20 kilometers. That's something that's well known. The size of a compact mass of quarks of this mass would be 20,000, that's 20 kilometers in meters, divided by 1,000 million, do you see that, meters? Which is 0.0002 meters, or 0.02 millimeters. That's pretty small, isn't it? Now, okay, that's 1.4 solar masses. I said you don't get a black hole with that mass, but if you have 10 solar masses, then you've actually got more mass, and you've got to multiply that by the cube root of 10 over 1.4, and it doubles the size roughly, and it's 0.04 millimeters. So, okay, that's very, very, very small, but it's not actually a singularity. Now, a complete warning, shall we say. This may be completely untrue, but I thought it was rather fun. And it's in the transcript. I have not found that calculation anywhere, and I've searched quite hard. So, as I say, it's highly unlikely that I'm right, but it's interesting. And I think I am really right, and other physicists will totally agree, if you ask them carefully, that there's no singularity at the heart of a black hole. What there's there, we can't tell. What I've told you is probably as good as anything. So just accept it for that. How big is a stellar mass black hole? Well, I gave you a formula, which I don't want you to worry about. But basically, if you put in the numbers, put the mass here, 8 solar masses, that's one solar mass is 2 times 10 to 30 kilograms, so that's the 8. So that's the mass coming in. You know what C is. G is the universal constant of gravitation. It's not that complicated. And out comes 24 kilometers. So that's the size of what's called the radius, the Schwarzschild radius, the radius of the event horizon of a stellar mass black hole. And that's why I said that there are probably quite a number of black holes that have sizes of the order of 10 to 30 kilometers, because that's the range that we would expect to have from stellar mass black holes. There's an interesting theorem. It's called the no-hair theorem, and that postulates that a black hole can only have 3 properties. Everything else about the objects that fell into it is lost. It can have mass, it can have electric charge, and it can have angular momentum, which is rotational energy, energy of rotation, like the Earth and the Sun have. Everything else about the matter that falls into a black hole is lost. Some controversy about that, because it does violate 1 or 2 bits of physics, but most people reckon that's right. So basically, only those 3 things: mass, charge, and momentum. Now, on the large scales, matter is neutral. Electrical forces, electrostatic forces, are enormous. If I had any hair, a little comb would pull it up quite easily. Far, far, far stronger than the forces of gravity. And if, in fact, matter wasn't neutral on the large scale, all hell would be let loose. It is. So we don't expect black holes to have any electrical charge. On the other hand, virtually everything in the universe has some rotational energy, angular momentum. Our Earth is spinning. The Sun is going around every 25 days or so. Everything is going around the centre of the galaxy. So it is highly likely that virtually all black holes, when they're formed, will be spinning. And that makes them much more complicated, and they form what is called a Kerr black hole. And this is more complicated. It's got several parts. The middle bit is just like a normal black hole, but that's surrounded by another part called the ergosphere. And beyond that is the bit where things are sort of more normal. Apparently you can get into the ergosphere and get out again. If you go over the event horizon in the middle, that's it. The rotating black hole drags the space around it. It's called frame dragging. And in fact, there is a satellite that's trying to detect any frame dragging due to the rotation of the Earth. I think there's been a problem with it. So that's something that physics predicts. And as I've said, matter can escape from the ergosphere, and actually in doing so, it can actually remove some of the angular momentum. So it's called the Penrose process. Have you heard of Michael Penrose? Famous physicist, mathematician. It's after him, he worked it out. And so in principle, a black hole could eventually become sort of static, and a simple one. But to be honest, most of the black holes I would expect that exist out there in the universe, in the galaxy, are going to be rotating ones, which makes them more complicated. Einstein's theory says that the singularity is no longer a point, it's a torus, it's like a little donut. Well, you can believe that if you like. Okay. So, now look, every holiday, like now on half term, at Jodrell Bank, we do Ask the Astronomer, where one of us stands up for half an hour and tries to fend off all the questions from the kids. It's always the kids that ask the most complicated questions, by the way. And what mostly boys like to ask is, what would happen if you fell into a black hole? Well, your prognosis isn't very good. It's the first thing to say. But we think we know, and there is a name for this. It's called spaghettification. And if you don't believe, I haven't made that up. If you type that into Google, it's in Wikipedia, and it therefore must be correct. In fact, it comes from a book that you'll all have read and understood called A Brief History of Time by Stephen Hawking. And he says in that book, if you go into a black hole, it's a bit like turning into spaghetti. So that's the name, spaghettification. If you don't like it, there is actually another name for it. It's called the noodle process. And again, that's not making it up. It is absolutely real. And it tries to explain what actually happens. So let's consider an astronaut who's foolish enough to decide he will fall into a black hole. And there he is. He's quite slim and lithe, but you know, he's a fairly normal astronaut. He could be in a spaceship, it doesn't matter, but he's doing that. Now, obviously, he's going to free fall in towards the black hole. And if you're in free fall, you don't notice straight gravity. You know, you're just there. You are falling, but you don't feel as though anything's happening. But there's a problem. As you begin to come near the so-called event horizon, and what happens depends on how big it is, by the way, we'll come to that, you get squeezed. And it's the result of tidal forces. The point is that in this case, your feet are nearest the centre of gravity of the black hole than your arms and your head. So the gravitational force here is bigger than here. And the effect of that is to put you on a rack, to stretch you. Now, look, we have that effect with the moon. If there was no moon, the oceans on the Earth would be a nice sphere, shall we say, you know, just gently surrounding the Earth. But because of the tidal forces of the moon, the gravitational field of the moon is a bit stronger on the near side of the Earth than the far side. And you know it makes the water form a bulge, both directions. So it becomes a bit elliptical. Instead of round, it becomes elliptical. And that's the effect of tidal forces. We call them tidal forces because it causes the tides on the Earth. So it is a quite generalized thing that if you are close to a massive object, tidal forces can have quite major effects. And there's one example which we'll come back to in the next lecture, which is the little satellite Io of Jupiter. It's very close. The tidal forces basically make it do this by about 40 meters. It squeezes it and pulls it, and the friction caused makes the interior of Io molten, hence you get volcanoes. So it's not something specially to do with black holes. It's just that because the gravity of black holes is very great, the effects are large. So here we are. In this case, we're quite close to the event horizon, and we're being squeezed and stretched. If the black hole wasn't very big, say an 8 solar mass black hole, in fact, I think the stretching would be such that 400 kilometers away, we wouldn't survive. But the bigger the black hole, the less the relative effects are until you get quite close. And if it was, say, a 1,000 mass black hole, you could actually pass through the event horizon and still be alive. You could see the universe around you. Nothing stops light getting into the black hole, it's just it can't get out. Things will look very distorted because the gravity of the black hole distorts the space around. But you could still see outwards. You will live longer, as I've said, if the black hole is very big. 8 solar mass black hole, you'd be dead 400 kilometers away from the event horizon, which is only 24 kilometers in radius. So that's not a good thing to try. But if you had 1,000 solar mass black hole, as I've just said, you could pass through the event horizon and still be alive. But not for long. In fact, it's about 7 seconds. How much of that? You might be alive for 1 second of that. It would take 7 seconds before you were totally spaghettified and became part of that quark mass, possibly at the center of the black hole. What would we see from outside? Well, here's the spacecraft. It's got flashing blue lights. It's going around. You've all seen Close Encounters, haven't you? Okay. Now, what would we see if such a spacecraft went towards and into a black hole? Now, the first thing, obviously, is that it would be accelerated under the gravitational forces, and that will cause an increasing Doppler shift. But if it had incredibly good, this has got a warp drive, so there's no real problem. It had very, very good engines. It could actually travel towards the black hole, let's say at a constant speed. So Doppler shifts don't come in. But even if that's the case, as it got nearer the black hole, those flashing blue lights would become yellow, and then orange, and then red. And that's because of something called the gravitational redshift. The light coming from those little flashing lights has got to climb out of the potential well, the gravitational field of the black hole, and in doing so it loses energy. And we have exactly the same thing to do with gravitational redshifts from the Earth, and very, very similar, something called gravitational time dilation. And if these little lights were flashing once a second, the nearer it gets, the rate at which we'd see them would get longer and longer and longer, until eventually, as it sort of gets close to the event horizon, it would just freeze effectively. Well, that's not going to happen ever, but it wouldn't be a nice thing to try and do, but we would at least see them on the way in, if not once they've got inside. How can we detect black holes? Well, it ain't very easy, to be honest. Can you see the one in here? It's jolly dark, isn't it? Look, I have to put my hand up. It's not actually a picture of a black hole. I tried very hard. I couldn't find one. But I did find a picture of dark matter. So that's a picture of dark matter. OK, now, right, you could not see one if it was in isolation, basically in the middle of nowhere. However, if one was quite close to you and it was in front of a rich star field, then you probably could. You'd see a silhouette, and that's a nice picture, simulation of course. There's the Schwarzschild, the event horizon of the black hole, but around it, because of its gravitational forces, it's basically distorting the light from the stars and the gas behind. It would look very, very pretty. And that's, in fact, another image. What you would see if there was a black hole in front of a nearby gas cloud. Now, be a bit careful. That looks quite big. If the black hole silhouette was the size of the moon, which it need to be to make it look obvious, we'd have to be about 2,750 kilometers away from it. Unless you were moving fairly quickly, that's not a very safe place to be. So it is highly unlikely that we'd ever actually see a black hole in silhouette like that. This is a rather lovely galaxy, and this is a simulation of what would happen if a black hole were to pass between us and it. And it distorts the image most beautifully as it goes past. Lovely to think about, probably never ever to be seen. So I'll just let it go through the center of the galaxy again. Points turn into lovely arcs and rings. They're called Einstein rings. But there is a way we can detect black holes sitting in the middle of nowhere in our galaxy, and it's by something called gravitational microlensing. And the point is this: we've just said that black holes can distort space. In fact, they curve the space around them so they become rather like a convex lens, like a magnifying glass. And if you hold a magnifying glass up to a distant light, it will look brighter because the light's concentrated on your eyes, as you sort of see here. In fact, the single image of the star turns into two images, but with our limited resolution, it still looks like just a brighter star. So this is what would happen if we have a distant star and a black hole is moving across in front of it. As it gets in the line of sight, it curves the light around it, and the star, which we say is microlens, becomes brighter. And then it fades away again. So this, in principle, is a way that we can detect little black holes just floating around in our galaxy. And it has been done. This is a picture of a star field taken from the ground in 1996, and that's probably a combination of two stars. This is the picture, November the 15th, and it's pretty obvious that that's brighter, isn't it? So something there has been microlensed. If you know what the brightness of the star was originally, which they didn't know then, you could sort of work out the mass of the thing that was doing it. And to do that, they got the Hubble Space Telescope. This is HST Wide Field Planetary Camera 2. We're now on to Planetary Camera 3. And it showed that this bright bit here was in fact two stars, and that was the one that was being microlensed. So knowing that, they can find that the object's got to be fairly massive. If it was a star, we would see it. Because we don't see it, we assume it must be a black hole. These things, by the way, are called machos, and that's the word there. Massive, compact halo objects. And black holes are one of these. There don't seem to be an awful lot. I think they thought there might be lots and lots of black holes wandering around the galaxy. Doesn't seem to be the case, but there are at least some. So there we have a macho event, discovering the presence of a black hole simply because it forms a gravitational lens. Sorry, wrong button. If you have a black hole which has a companion star, that's in a binary system, everything becomes much, much, much easier. First of all, a black hole's got gravity. It can pull matter from its adjacent star, its companion star, onto it. And if the thing is rotating, the angular momentum causes a lot of friction. The temperatures can go way up, and you get what are called X-ray flares. And that's the sort of idea. And in fact, many of the black hole systems that we now know of in our galaxy have been originally observed and highlighted by an X-ray flare. The material here is basically spinning around. As it gets closer and closer in, it goes faster and faster. A bit like water, you know, as it spirals in towards the hole at the bottom of a bath. Same thing. That's what happens. The friction gets enormous temperatures, and you get these so-called X-ray flares. Sometimes sufficient mass can concentrate, it sort of blows up as well. So that can actually highlight what happens. Now, again, if you have a binary system that we think might have a black hole around it, we can observe the motion of the companion star and show there's a star, a black hole, next to it. This is the idea. If you have a binary system, the star and the companion black hole both co-rotate round their common center of gravity here. So what happens, you can see it here. I can't make the black hole totally black because you wouldn't see it, but you get the idea. That's the black hole going around. There's the star going around. We can't see the black hole, but in principle we could see the star moving. And it's exactly the same technique that we use to discover the presence of extrasolar planets. So if this is the barycenter, the center of gravity of the system, as the black hole goes around that way, the sun goes around, so it's always opposite the black hole, the star. And if it's coming towards us here, we get a blue shift. If it's going away from us there, we get a red shift. So we can see the spectral lines of the star shifting. This is, by the way, an incredibly over-pushed example, but basically at the top there you have what the lines should be, and we can measure that on Earth. Here they're shifted to the red, down that way. There they're shifted to the blue. In fact, the shifts are incredibly tiny, but nevertheless they're there. And from that, you can deduce how rapidly the star is going around, and you can also measure the period at which it's going around. That's all you need to know. If we know that, we can find the minimum mass of the two objects. In the case of stars and planets, because the planet's tiny, you can actually work out the planetary mass immediately. In this case, you can't. You just know the total mass of the pair of objects. But if we can see the companion star with our telescopes, we can say what type of star it is, and from that we can get a pretty good idea of its mass. If that mass is greater than 4 solar masses, i.e. you take the total mass, you subtract off the mass of the companion star. If what you're left is greater than 4 solar masses, and you can't see it, it'll be a black hole. There are several very good examples of these. Many of them have been first triggered by an X-ray flare. I'm very pleased to say that probably, if it's not the very best, it's the second best, is a particularly good one, and you'll see why I'm somewhat biased in this. It's also the nearest black hole to the Earth, so it has that advantage. The reason why I'm biased is because I discovered where it was. Didn't discover it, but here's the story. Ariel 5 was a UK satellite. On board was an X-ray detector built by the University of Leicester under Ken Pounds, Professor Ken Pounds. And in 1905, in August, they discovered the brightest X-ray flare that has ever been observed from the Earth. It was truly spectacular in X-rays. Now, the trouble was that in those days, and again, because it's in the days of black and white, they hadn't gone to colour by then, in those days, all they knew was it was sort of there-ish in the constellation of Monoceros. They didn't know where it was. So, in August, I was out at Jodrell Bank. I was the only staff member present. Everyone else was on holiday, it happened. And I got a call from Ken Pounds saying, look, we've just got this flare from somewhere in Monoceros. Will you use your telescopes to find out where it comes from? So quite excited, I went straight over to our Mark II radio telescope, which is the second big telescope at Jodrell Bank. And pretty all by myself, I think, I surveyed the part of the sky which is where they said the flare came from. And I picked up absolutely nothing. Well, happily, nobody else did anywhere in the world, because he'd obviously asked almost every radio observatory, every optical observatory, to try and find out where this thing was. A slight pity. We had an identical sized telescope 15 kilometers away, and we could link them together to make a very sensitive instrument, far better than a telescope just by itself. But we'd loaned that to another group for a week. So it was about a week and a half before we got it back, and we could combine the two telescopes. So with my research student and two of my buddies, we set out to survey the part of the sky where they thought this thing was. Now, in those days, it was the days of charts. We hadn't really got computers. Computers controlled the telescope, but not the data. And we had a chart that went literally the whole lab length from over there to over there, and this was where they said it was, in Monoceros. Where did we find it? 2 inches from the end. It was literally, I mean, we were dead lucky to get it. And in fact, we were the first people to discover the object that produced this great flare, Monoceros X1. And as a result, is actually given the name A0620-00, which is simply a shortened version of the position that we found. And very nicely, what is the top UK science journal, anybody? Thank you. The first paper about this discovery was obviously the Leicester one, and then immediately following that was ours, saying where it was. We also could tell something about the structure of what we were observing, and it was a bit odd. We honestly weren't able to interpret it. We didn't really understand what was going on, but it wasn't just a simple point source. That we did know. Anyway, we'll come back to that later, because that's a bit later in the story. However, that's been a great target of observations ever since. And we now know that the companion to the hopeful black hole is a K2 type star. Now, I better not say this, but it's OB something, something, something. OBAFGKM. Do you remember that, the sequence of stars, anybody? We're a G star, OBAFG. K is the next, fainter, and fainter means less massive. And the range of masses for K-type stars is 0.5 to 0.8 solar masses. So we know what the mass of that star is. The radial velocity is 460 kilometers per second. That's pretty fast. The period is that. From that, we can get the combined mass of the K2 type star and the black hole. And it turns out that if you subtract 0.8 solar masses off 10.5, you find, sorry, didn't mean to do that, you find that the accompanying object is about just under 10 solar masses. And that's way above the 4 solar mass upper limit for a neutron star. So as we cannot see that object, it really has got to be a black hole. And the reason why that flare was the strongest that's ever been observed is because it's quite close, 3,500 light years away. Now, I said that we couldn't really understand our observations, but we returned to this in 1999, and by then we knew a lot more about this type of thing. We actually called them microquasars. And we could see that our observations actually showed that there was a jet of material, or a blob of material, working its way outwards from the position. And so we wrote another paper using the same data from 1975 in 1999, which is probably a bit of a record. So anyway, that's the sort of thing that we discover and find out about solar mass black holes. Now, right at the other end of the scale, we have supermassive black holes. And the story of those actually also began at Jodrell Bank, when a pair of telescopes, the then Mark I telescope and a small one, discovered some radio objects that were tiny in angular size. They looked like stars. They were given the name quasar. Have you heard that term? Quasar. Quasi-stellar objects looking like a star. When the precise position of the first of these was shown, and the Hale telescope, the 5-meter in America, took a picture, it showed there was a little jet sticking out. It wasn't a star. Then Martin Schmidt took the spectra, and he took ages to understand it because the lines were redshifted by 16%. That was unheard of. It meant this object was 2,500 million light years away, which is a long way. Now, it was very bright. I've got a 12-inch telescope at home. I can see this object with my own eyes, just with a small telescope. Can you see, if it's very bright and an awful long way away, it must be producing lots of energy? Is that fair enough? And if you did the sums, assuming the energy went out in all directions, it was amazing. How could you get that amount of energy created or generated? Now, it turns out that that jet is actually a beam, and these things are little beams. If I had a big torch battery and a little bulb just stuck on the top, you could see that. If I put that same battery, same type of bulb, in one of those Durabeam torches, if I pointed the beam at you, would you agree it'd be much, much brighter? So these things are basically ones that we see because they're beamed at us. So the energy requirements aren't as great, but they're still pretty massive. And how does that energy come? Well, what you may not know, nuclear fusion, which is the best technique we can think of generating energy here on Earth, releases actually it's 0.7% of the rest mass energy of matter, which we think is pretty good. But falling into a black hole releases at least 10%, and if, as I've just been saying, the black hole is rotating, that could be as much as 30%. So black holes, or falling into black holes, is an incredibly efficient way of converting mass into energy. And if you do the sums, and I've done them in the transcript for you, you find that black holes don't need to gobble up too many stars to keep shining as brightly as they do. So for ages we've thought that these supermassive objects at the heart of these quasars would have to be black holes. We didn't know what the mass was there, we thought there had to be a black hole there. So a black hole could provide the energy to make these things as bright as we can see across the universe. So, a couple of examples. We are an outlying, rather upmarket group of galaxies on the edge of what is called the Virgo Cluster. That's the heart of a big supercluster. Virgo Cluster is sort of like the City of London, and then you have some smaller things around the outside, let's say Reading, they're sort of medium-sized clusters. Where's a posh place not far from London? Small? Oxted, yes, okay. Well, Oxted, that's a little posh place. That's like our own little local group of galaxies, all right? We're a rather nice little group of galaxies right on the edge, in the outer suburbs. Okay, now this is looking at the heart, and there's some massive galaxies there. One of them is M84. In the radio, can you see those little jets? The red is radio, the blue is X-ray, a lot of X-ray emission, that's what you get from these black holes, and the white bit actually is the galaxy you see normally. So this is a real candidate for a black hole, but it's been proven. This is a wonderful image. They took the very heart of it, the very heart of it is here. They put a slit, this is the Hubble telescope, across the heart, and as you came in from one side of the centre to the other, the redshift, or the shift in the light, suddenly became very blue here, blue shifted. The gas producing that light was coming towards us very quickly, 400 kilometers per second. Then it very rapidly went over, so there was a red shift. The gas on this side was going away from us at 400 kilometers. Can you see it means the gas is rotating round very fast? And you can work out the distance from the center, it's 26 light years. And if you do the sums, they're not very complicated, you get a black hole which might be 1.3 thousand million solar masses. So that's a supermassive black hole at the heart of a nearby galaxy. What about our own galaxy, the Milky Way? Well, we've known in the radio for a very long time that right at the heart of the galaxy was a very bright little compact radio source that we always thought might be the black hole at the center. It's called Sagittarius A. But if you look at the center of our galaxy visually, you can't see anything. There's so much dust. There are only two wave bands that we can now use to try and probe, apart from radio, the heart of the galaxy. One of those is X-ray radiation, and the Chandra satellite can also show a little bright spot here which corresponds to Sagittarius A star. That's where the black hole is, as seen in X-rays. This is an incredible image in the infrared. That's the other part of the spectrum where you can probe into the inner part of our galaxy. And the arrows have been nicely painted on the sky so you can actually see where Sagittarius A star is. Now, the resolution here is amazing, as good as the Hubble Space Telescope, but done from the ground. And very quickly, the reason that they can do this is that they fire a beam of sodium laser light up pretty much on the direction they're looking. That's up towards the Milky Way. That excites atoms in the high atmosphere that form what's called an artificial star. They can look at that light separately, and they can see how the atmosphere is deforming the image, and amazingly corrected in real time. So they're getting incredible resolutions in the infrared. So that's one telescope that can do it. Another one that can are the Keck telescopes up on Mauna Kea in Hawaii. And this is an image it's taken, and this is actually 8.6 arc seconds. But the bit we're interested in is just the middle sort of 1 arc second roughly square, this bit. And Sagittarius A star is right at the heart of that. And these are individual stars. And what they've been able to do over 15 years now is to plot the trajectory of the stars around a point at the center. The star represents, so I go back, the star represents where we think the black hole is. Now, can you see that green one coming in very fast? And can you see that yellow one that goes round? And I go back and just have another quick look at that. The green one comes in there. Can you see how fast it's going? And then goes out again. And the yellow one there, SO2, has done one complete orbit. SO16 has gone in and gone out. Those are two most interesting ones. That's a rather garish picture showing the whole results. But the important thing is this. Star SO2 orbits 15.78 years. Star SO16, that was the one that came in very fast and went out, that came within 45 AU of the galactic center, at which time it was moving at 12,000 kilometers per second. Now the point is, you can take that data and you can find out what the mass at the center's got to be. And it turns out to be 4.1 million solar masses. That's quite a new result. We now have a very good idea of the mass and hence size of the black hole at the heart of our Milky Way galaxy. And the last of these big ones, Virgo A, is the most massive galaxy in the Virgo cluster. It's got a jet, you see there, and a lovely radio image of it there. So when you get jets, you think black hole here. And again, they've observed the light from the gas surrounding it. Some is blue shifted, some is red shifted. You do the sums, you know how far away the gas is. 3 billion solar masses, which is probably the current record. So you can see we have solar masses over an incredible, black holes over an incredible range of mass. Now quickly, we recently, I say astronomers have recently discovered what we call intermediate mass black holes. In the southern hemisphere, and I was lucky enough to be down there in their winter and had wonderful views of this part of the Milky Way. This is Proxima Centauri, and Alpha Centauri down here. That's the nearest star system to us. Beta Centauri, they sort of point towards the Southern Cross. But if you sort of go left here, you come to that. Omega Centauri. It was thought to be the biggest globular cluster, which is a compact cluster of stars of our Milky Way, much bigger than any others. That's what it looks like. But in fact, we now believe, for several reasons, it is the remnant, the core, of a galaxy whose outer parts have been stripped off by the gravitational field of the Milky Way. And this is not a real diagram, but it's a hypothetical one. The observations imply that at the heart of it, just from the motion of the stars, there's a 40,000 solar mass black hole. And another one is an object called Mayl 2, which is down here, which was in fact thought to be the biggest globular cluster anyone had ever observed. Again, we now think it's the remnant of a small galaxy, and at its heart it has an intermediate mass black hole. 17,000 solar masses, and that's the sort of spectral line information that gives you the information. So we have solar mass black holes, we have intermediate mass black holes, 40,000 or so in these remnants of small galaxies, and we have these supermassive ones at the heart of big galaxies. And that's a sort of a plot of the whole sky showing the ones that we think we know of. The solar mass ones are the red ones there. See a lot of them along the Milky Way, that's where stars are, and the blue ones are the supermassive ones. So finally, black holes are not totally black. And this is perhaps some of the best thing that Stephen Hawking has ever done. The reason why they're not totally black is actually very complicated quantum mechanics, and everything you say is probably not quite right, but I'll do my best. Essentially, in the gravitational field at the edge of the event horizon, you can create virtual particles. They're called particle-antiparticle pairs. They come into existence, providing they disappear again before Dr. Heisenberg gets upset. It's called the Heisenberg uncertainty principle. You're okay. And that can happen. But three things can actually happen. It's possible that both particles go into the black hole, and then they just annihilate, and that's it. Nothing happens. Both particles can escape from the black hole. Again, nothing happens. But also, it's possible, rarely, for one particle to escape and the other one to go in. And this is sort of trying to explain what's happened. This is, sorry, didn't mean to do that. This is time going that way. So this is a black hole, and these are things being formed at the edge, and you see occasionally one escapes and one goes in. And when that happens, the one that escapes becomes real, and that has real mass or energy. The one that goes into the black hole is saying, oh dear, I shouldn't have any of the mass I've got because, you know, I'm virtual. And it actually has to become negative in its mass energy in order to keep conservation of energy. And so, effectively, it's taking a bit of mass away from the inside of the black hole. So in that sense, the black hole can radiate and hence slowly evaporate. So the black hole absorbs the negative energy, loses mass and appears to shrink. The rate of power emission goes as the inverse square of the mass. Now, no one has seen this happen yet, as we'll come back to. The particles that leave the black hole are called Hawking radiation, as I've just said. And he showed that black holes will evaporate in time, and that could be eons for large ones, as we'll see. And just a quick look there, you might just spot little bits of emission from the black. Do you see that one flash up? Well, whether we'd see that or not, I don't know, but that's the sort of idea. Now, look, last equation. Black holes have an effective temperature. And basically, the greater the mass which is underneath, the lower the temperature. That's all you have to know. A black hole can only radiate away if its temperature is greater than the temperature of its surroundings. So here is a little example of something like that. Now, these are virtual drinks, because we're not allowed to bring them inside. This is very hot. It says so. It says, this drink is very hot and may scald. Do not drink until cold. So that's a hot drink. And this is a very cold one, all right? That says, basically, best served ice cold, perhaps because your taste buds don't work when it's very cold. Now, look, the point is, if I put these two down, it is obvious that the hot one is going to cool down and the cool one will warm up to ambient temperature. Is that fair enough? Now, most of that heat transfer is done by convection, little air molecules hitting them. But even if you put these inside a little glass box and evacuated it, they would still come down to equalize their temperature by radiation, because that's one of the other ways you can transfer heat. Look, you get near a nice fire, can you feel the radiant heat? So, a black hole can gain or lose energy depending upon the temperature of the radiation around it. And of course, that is not zero. They can only lose mass when their temperature is less than their surroundings. The universe has a temperature of 2.73 degrees, remember that? Cosmic microwave background. Only black holes whose mass is roughly that of the moon could be losing mass now. If you have more massive black holes, their temperature, an 8 solar mass black hole, it's nanokelvin, way, way, way below the surrounding radiation. So in fact, that black hole will be absorbing radiation from space and actually getting more massive. But of course, as time goes on, the universe is expanding, as we now believe, at an ever faster rate. And eventually, such black holes could begin to evaporate. we may be able to produce these micro black holes in the Large Hadron Collider, and they would actually evaporate in 10 to the minus 80th of a second, so don't worry about them. That could happen now, but we haven't yet detected. But that's the sort of thing that might be seen at the Large Hadron Collider. If low-mass black holes were created at the time of the Big Bang, that's the only time we know how to make them, it is just possible they could be basically annihilating now. And here we see, when they finally evaporate, you get a massive burst of gamma rays. Now, it turns out we do see massive bursts of gamma rays. They're called gamma ray bursts, and I'll tell you about those in the lecture before Christmas. But we believe they're associated with the mergings of neutron stars or black holes, nothing actually to do with the evaporation of a black hole, which is a real pity because we don't yet seem to have seen one evaporate. And Stephen Hawking says this is very sad because if we had, he'd have a Nobel Prize. And that's the end. I would just like to say, do you know where the Nobel Prize for Physics was awarded to this year? Manchester. That was good. So, thank you very much for listening.